Hi all, this is Mahesh Bhosle, third year PhD student at University at Buffalo. I'm excited to present our work FairLLaVA, Fairness Aware Parameter Efficient Fine Tuning for Large Vision Language Assistants at CVPR in Denver, Colorado. This work is in collaborations with researchers from University at Buffalo, University of Kashmir, Accenture, and Harvard Medical School. For motivation, we start by asking question, is your vision language model fair? The answer is no. We evaluate multiple multimodal LLMs separately for race, age, and gender groups on medical report generation task. The results show that report quality is not uniform. Some groups get better performance than others. This unequal performance is what we call fairness gap, and it motivates FairLLaVA to promote balanced performance. Previously, methods have been proposed to reduce fairness gaps in LLMs, but those methods focus on frequency of sensitive words related to demographic attributes in the output itself, which is not applicable in this setting because medical reports do not contain such sensitive information. So, what exactly is fairness gap? So, put simply, it is unequal performance of the model dependent on the demographic or sensitive attribute. Such gap exists because mutual information between hidden states of a model and demographic attribute is not zero, even though model never sees any demographic attribute during training. Such spurious correlations can be harmful for fairness, so idea is to reduce the fairness gap by reducing this mutual information. So next question is, how can we measure the fairness? So here we measure fairness not only by overall performance, but by how evenly the model performs across demographic groups. We see in our experiments that there is a trade-off where model that performs worse overall has lower fairness gap. Therefore, a fair model should not improve fairness simply by making every group worse. So we define fairness gap as the difference between best performing and worst performing subgroup, but we use equity scale metric which rewards both high overall performance while penalizing large demographic gaps. We therefore minimize mutual information between hidden state representations H and demographic attribute A. Since exact mutual information is hard to compute, we may not because we may not know exact joint distributions over changing hidden states and demographic attribute. Instead, we use a tractable bound, upper bound, with a demographic attribute classifier, DAC. The classifier tries to predict the attribute and model is trained to reduce demographic mutual information available in the hidden state. The DAC is learned with normal cross entropy loss that maximizes log likelihood. So finally, demographic mutual information itself is learned over batches by choosing one sample as positive and rest as negative, similar in principle to contrastive training. So our method FairLLaVA has two stages. First, we perform a standard visual language alignment stage where image embeddings are aligned with language model for report generation task by learning a projector. In the second stage, we add lightweight LoRa adapters and introduce fairness-aware fine-tuning. The key idea is to reduce demographic information inside the hidden representation while still preserving the report generation ability of the model. So LoRa adapters help us to do this in very efficient way. So in the results table, we compare FairLLaVA with multiple open source medical vision language models and fairness baselines. Across race, age group, and gender, FairLLaVA generally reduces the performance gap between demographic groups. This means that model becomes more balanced rather than performing well only for certain subgroups. Next, in the next table, we report equity scale metrics. These are important because they combine two goals, maintaining strong clinical report quality while reducing demographic disparity. FairLLaVA improves these equity scale metrics as well across several metrics, showing that method does not simply sacrifice overall performance to look fairer. Instead, it preserves useful report generation while reducing subgroup gaps. This example compares generated reports for different demographic groups with same ground truth finding. The baseline reports can miss or inconsistently describe clinically important findings. FairLLaVA, on the other hand, produces reports that better preserve the key finding across groups while reducing demographic dependent variation if present in the generated text. So, to summarize, FairLLaVA is a lightweight, parameter efficient method for improving fairness in vision language medical report generation. By minimizing demographic information in hidden representations, it reduces subgroup performance gaps while maintaining clinical generation quality. Thank you.